This video was originally going to be a rather dry tutorial, but I wanted to make something big as an example for what you can really do with circuits, and so I decided to build my own take on a belt printer. Then I forgot I was supposed to be making a tutorial and just kept on adding features, so now this video is about building this thing. I thought of talking about a bunch of practical designs for use in-game, but if you care about that sort of thing, you can go read the wiki. I want to talk about this thing. You're going to learn about the true uses of circuits, making things that have absolutely nothing to do with beating Factorio. This printer might seem incomprehensible, but once you know the constituent components, you'll find it becomes at the very least comprehensible. If you don't know the basics already, watch my 3-minute tutorial, or if you don't care about understanding the components at all, just skip to here, I guess. Now, if you think you know a little digital logic, forget it, because combinators are mostly their own thing. They're closest to something like hardware programming, and that's because you actually need to worry about the timing. So imagine dropping 2 marbles down 2 different chutes, one's shorter and one's longer, and then acting surprised when they don't shoot out at the bottom at the same time because all your calculations after that assume that they would, and now everything's screwed up. Like this lamp that's set to turn on when the green signal equals 2. Let's say we have 2 signals, the green signal and another signal we want to turn into the green signal, so we send it through an arithmetic combinator and tell it to come out as the green signal. Now if we connect these wires, they're added together, goes into the lamp, and boom, it turns on. But that's using a constant combinator, which is continually outputting its contents every frame. If we replaced it with a push button, no matter how many times we hammer it, the light will not turn on. But why? Well, Factorio's broken up into 60 update ticks per second. Every 60th of a second, the game updates, and that's really important because it takes 1 tick for a combinator to do any sort of calculation on its input and output the result. So because the push button sends a 1-tick pulse of data, what's happening is the green signal with a value of 1 is reaching the lamp, then disappearing, and because the coal signal we turned into the green signal needs to pass through the combinator first, it arrives 1 tick later, also with a value of 1. They never meet up, and they never add together and become 2. Going back to the marble metaphor, if we want them to meet up, we can either make something that holds 1 marble there until the other one arrives, which would be a memory cell, or we could do the much easier option, and that's just to make both chutes the same length. If we force the original green signal to also go through an arithmetic combinator that does nothing but add 0 to it so it outputs the exact same thing we put into it, suddenly the lamp lights up for the 1 frame now because the data is synchronized. This 1 tick cost for data to traverse a combinator is probably the single most important thing to learn if you want to understand advanced circuit networks. Also, the push buttons are from a mod, but they should be in the base game if you ask me, because they're quite useful. Anyway, now that you know that it takes a 60th of a second for any signal to travel through a combinator, we can move on to the powerhouse of Factorio circuits, the memory cell. Memory cells, as the name implies, holds memory. You know how that lamp kept turning off? Well, if we feed the output into a memory cell, then push the button, suddenly the lamp stays on. And that's because the memory cell's captured what we put into it and is now outputting at every tick just like a constant combinator. Though if you push the button again, it turns off, and that's because we set it to turn on when green equals 2, and now it's 4 because we put another 2 into the memory cell by pushing the button. The way a memory cell actually works is really simple. We have a decider combinator with some condition that's always true, and we set it to output everything as input count. Then we wire its output back into its input, preferably using a different wire color, and suddenly everything you put into it stays inside. Now that you know about update ticks and the 1-tick internal delay, you should be able to understand what's going on here. The cell is taking input, then spitting it out 1 tick later. Its output immediately gets fed back in as input, and then that gets spit out again 1 tick later. It's just a continuous loop, constantly regurgitating what we put into it until the end of time. Or until the condition is no longer true. Usually for memory cells, you'll have something like if R equals 0 as the condition, with R standing for reset, but any kind of signal will work. That's because the moment we press this button containing an R value of 1 and feed it into the memory cell, all of our memory disappears. And that's because even if it was for only 1 frame, we've blocked it from outputting anything. That means it won't have any input for the next tick, and the cycle's been broken. If you don't understand it yet, I'm sure it'll make more sense when I talk about the next component, the clock. So we know what happens if we put a pulse of data into a memory cell, but what happens if we use a constant combinator instead? Well, this. What's happening is that the memory cell is behaving just like before, outputting its contents every frame, but now that we've wired in a constant combinator that's continuously outputting a value of 1 every tick, it's being added to the contents of the cell. It spits out 1, meets with the 1 coming from the constant combinator next frame, then outputs 2. That goes back in as input next frame, and once again meets with another value of 1. Now there's 3 inside. It spits that out, and would you believe it? While that 3 is being fed back in, another 1 has appeared, and now there's 4 inside. So on and so forth, every frame 60 times a second. It doesn't need to be 1, you could make it at 100 each frame if you wanted. All that matters is that you understand the sort of tick-by-tick nature of these things. Hopefully I won't lose you if I show that we could run a clock off of another memory cell, because just like the constant Combinator, it's outputting its contents each frame. It just doesn't have the extra input being added in like the clock. Now, as you can imagine, having something that increments by 160 times a second is very useful, and that's because if you wanted, say, a lamp to flash once a second, well, we just make it so the lamp turns on when t equals 1. However, t just keeps getting bigger and bigger. Yeah, we could feed it through an arithmetic combinator, take the modulus of 60 and then use that, but it's much easier if we just take the clock itself and set it to output when t is less than 60. Just like the reset signal before, as soon as t is over 59, the condition won't be true anymore and the memory will vanish. But because it's continuously getting an input of 1, it'll start right back up again, resetting itself every second. I cannot stress enough just how important understanding this interaction is for doing anything even remotely complicated with circuits. Just like real computers, being able to hold information in memory is pretty important, and so is having a constant clock to push everything along. A computer without a clock is like a car without wheels. Needless to say, not a very useful car. Well, that's that covered, but there's still a few things you've got to know before you're ready for the horrors that await. This next one's pretty simple though, AND gates. And this is why I tell you not to think in terms of conventional digital logic gates, because here, to make something turn on when this and that are active, we just make two decider combinators output one of a signal when the signals we care about are present. I usually use the green checkmark signal. Then we just have another DC that checks to see if there's two check signals and outputs another signal when there are. Now we've got a light that turns on only when both of these constant combinators are on. If you wanted to turn on only when 10 different signals were present, you just need 10 combinators and another one to output when all 10 are outputting one checkmark. To make an OR gate, just make it so the final combinator works if any of them are outputting checkmarks. All of this stuff is important, I swear. Next we've got latches. Let's say we wanted to control what color would be sent to this lamp. Yes, we could control it using a bunch of constant combinators and turn them on or off, but as an example, let's just say we wanted to do it with push buttons. Well, knowing what we know about memory cells, let's make a memory cell that will hold that color when we push a button. That's our latch. But wait, if we press another button it doesn't work anymore, and that's because the previous color is still in there, so we need to get that out before putting the new color in. We can solve that by adding a reset signal along with the button press, but then it blocks the color we want from being added too. Remember, it takes one tick for a signal to go through a combinator, and we can actually use that to our advantage here. If you make an arithmetic combinator that takes in that button's colored signal and does nothing to it, the color signal will arrive after the reset signal. Most importantly, the AC only outputs that color signal, so the reset signal isn't coming along with it. Just make sure you separate the wires or something like this will happen. We can do it smarter though. We don't need a combinator to isolate every color signal, we only need to remove the reset signal, and that brings me to signal sanitization. So you can have lots of signals on one wire, and sometimes there's a bunch of signals that you don't want on there. The easiest way to filter out only the signal you want is to put it through an AC, multiply it by 1 or add by 0, and then set it to output the signal you want. That works, but what if you need multiple signals? Well, you can make an AC for every signal you want and add them together at the other end. There, all nice and isolated. But what if there's 20 signals you want? Are you gonna make 20 combinators? Instead of filtering all the signals you do want, filter out all the signals you don't want. That's easily achieved with just two combinators. The first one multiplies each signal by 1 and outputs each signal. It's a delay, you've seen it before. But the next one takes the signal you don't want, multiplies it by -1, and then outputs it onto the same line. Because you're letting everything through the first combinator, including the signal you don't want, but you're also taking its inverse in parallel and outputting it onto the same wire, they cancel each other out. Now the offending signal is totally gone. You might think that the other combinator isn't necessary, but remember, because we need to multiply the unwanted signal, it requires one tick to compute. That means that if we didn't have this extra combinator, they wouldn't be synchronized anymore. They'd still cancel each other out if it were continuous, but when the signal appears, it leaks through for one tick. Then when it disappears, its inverse appears for one tick, as demonstrated by these alarms that go off when the fish signal appears as +1 or -1. Isolating and operating on only the signals you want is a major part of circuits, since you only get two wires to put everything on, but once you know the tricks, it's pretty easy. Alright, here's something random. Literally, it's a pseudo-random number generator. I'm not going to go in depth of why this thing works, but I feel like I should mention it. Broadly, it's akin to a linear feedback shift register, but it's probably easier to accept that it just runs on some eldritch magic. This thing is how I kept my truck spread apart in my Factorio City video, and if you want it in a smaller range, just take the modulus. To spice this tutorial up, let's set this inserter to insert this nuke only if the number is ever boobs. Now I know one guy is gonna be like, but modulus is a biased operation and not ideal for pseudo-random. Well yeah, but it's easy, and I really doubt you need a perfect distribution for Factorio of all things. Okay, this is probably the first thing I'm gonna talk about that I think is actually a bit complicated. It's about bits. It's something called bit packing, but you could also call it encoding and decoding. Basically, it's a concept of packing multiple smaller numbers into one bigger number. I did this in the second part of my space exploration run to fit both the number of capsules and cargo sections into a single signal. It might sound scary, but if I have 11, 33, and 55, and I wanted to put them all into one number, I'd just make something like this. As a human, it's easy to see where the numbers we want are, but to do it mathematically, we first need to make the number. That number is just 11 times 10,000, plus 33 times 100, plus 55. So we've got our packed number, now to unpack it, and to do that we first divide by 10,000. Factorio doesn't have floating point arithmetic, so only the whole number remains and we've extracted 11. The second one is a bit tougher though. If we divide it by 100, we get 1133, so how do we get rid of the 11? Well, we take the modulus of 100 and that leaves 33. If you don't know the modulus operator, think of it as dividing by 100, then taking the remainder. Now to get the 55, we take the modulus of 10,000. That's how we can fit 3 different 2-digit numbers into a 6-digit number. Obviously, if one of these numbers exceeds 99, we'll have a problem because it'll leak into the other numbers. That's called integer overflow, so just make sure you're not trying to fit a number larger than the space you've allocated for it. Hopefully you can understand that as we make it much scarier by actually packing bits. I'm going to assume that most of you at least have a cursory understanding of binary, but I am going to point out that Factorio uses signed 32-bit integers for its signals, so the maximum and minimum values you can store is this. We have 32 bits, so let's say I wanted to fit 8 4-bit numbers inside. That means they can be between 0 and 15 each. Here's our 8 numbers. If we smash them together, it'll look like this. It's harder to read, but conceptually it's no different than what we did before. But to actually get it out, we need to use these scary operations. They're called bit shifts, and they go left or right. If we bit shifted this number right by 4, it'll look like this. Well, it would actually look like this, but let's ignore the technicalities. We've effectively sliced off the bottom 4 bits, just like we did by dividing our decimal integer before. Generally speaking, each shift is like multiplying or dividing by 2, but it gets complicated with negative numbers, so let's ignore that. Now to isolate the 4 bits we want, we need to get rid of the rest. Instead of taking the modulus, we do the AND operation by 15. It sounds scary, but all it does is compare a number with 15 in binary bit by bit and output a 1 in that place if they're both 1 and a 0 otherwise. What that looks like is this. Wow, everything we don't want is 0 now, and all that's left behind is our 4-bit range. We in the business call this a bit mask, but the end result is we've extracted the 4 bits we want from that big mess. You might wonder why I don't just take the modulus. Well, that's because using all 32 bits of a signed integer means that it's possible for the number to become negative, and Factorio uses arithmetic bit shifts, whose intricacies I'm not going to go into, but modulo won't give the right value if it's negative. Same reason we're doing bit shifts instead of multiplying or dividing by powers of 2. Why would we even want to do this? Well, remember when I showed how annoying it is to isolate the signal you want if there's more than one? Well, this way you can combine them into one signal as long as you're fine decoding it later. But the main advantage is just being able to fit lots of information in one signal. It's unlikely you'll ever need to do this, but it's vitally important that you understand this to understand the printer. Okay, last thing I want to talk about is this shift register. It looks really scary, because it is. If you feel like you can't understand what it's doing, don't feel bad. I designed this like a year ago and still had to remind myself how this damn thing worked. But first and foremost, it's just a bunch of memory cells chained together. What it does is every second or so, it sends a pulse to wipe the memory cell, but before that, it also sends a pulse that allows this other combinator to output its contents to the next memory cell. You can see the data represented by the lamp, and every pulse it travels down until reaching the end and disappearing. What we've essentially created is stack memory, and now we can repeatedly push more and more into the stack as long as we care to add the cells to hold it. We can even wire the end to the beginning to make it just go around and around. The technical term for this is a ring buffer. The green wire carries the reset signal, and the red wire is for the actual memory. The memory cell works as long as the reset condition isn't present, but it also feeds into another DC that only outputs when the reset signal is present. Then that feeds into the next cell in sequence. That's controlled by a clock, and you see this feeding into the green wire, but it's also going through this arithmetic combinator that takes the inverse and puts that onto the wire one tick later to re-enable the memory cells. Yeah, it's a bit complicated, but very useful. Before we move on to the big one, I'm going to show you some smaller applications of these components. Like, have you ever wondered what the actual throughput of your belts is? Well, even if you haven't, I'm going to tell you anyway. So it seems straightforward. If we set the belts to read mode pulse, it'll output one of that signal for every item that passes the belt. That's great, but it appears for one frame then disappears. Not very useful. So what if we added a memory cell to hold that data? Well, it would just keep going up and up and up, but we're on the right track. If we add a clock and set it to cycle every second, aka 60 ticks, and reset the memory cell every time the clock returns to t equals 1, then we'll be able to capture the total throughput per second. Except, yeah, that's not exactly nice to read. But if instead of simply resetting the memory cell, we push this data into another memory cell after that one's collected a second's worth, well, that's certainly how many items pass the belt in a second, but it's not exactly satisfying, is it? We want to see the nice clean 45 items per second per belt. To do that, we'll need to run an average. What if instead of one memory cell, we used our shift registers? That way we could hold several seconds worth of data and take the average, which will smooth out any oscillations. The ACs are just to isolate the output onto a new wire so we don't create a feedback loop by adding together the data of multiple memory cells. And there we have it, a finished display for the average throughput every second. If you don't get it, I'll be putting all the blueprints from this video in the description. We can make it faster by reducing the clock cycle and some minor adjustments of the cells, but if you make it too fast you'll start losing accuracy again, so you'll need to add even more registers. If you really want, there's nothing stopping you from having 20 registers with a cycle of 3. That's just one example though, how about one more? You know those Nixie tubes currently displaying the throughput? Yeah, they're from a mod. So what if we wanted to know the numerical display in the base game? Well, here's the easiest way. We'll take a bunch of lamps and set them to light up when a certain signal is present. Each lamp has its own unique signal, and if we wanted to display, say, 5, we'd output all of the signals for those 10 lamps to light up onto the one wire connecting them all. Then only those lamps will light up, showing us the number. To display any input number, what we'll need to do is make a constant combinator for every number from 0 to 9 that contains the unique signals needed to light up the lamps for that one number, and have only that CC outputting its contents when the number equals 1, 2, 3, and so on and so forth until we've got this. That'll work. Then to make it work with bigger numbers, we just add some extra ACs to modulus the input number by 10 and send it through to that digit's display, but also divide it by 10 and send it to the next digit, effectively slicing off the digit that we just read. So that's something, but it's really bulky. I mean, 10 decider combinators? It's almost as big as the display itself. Yes, there is a smarter way, and here it is. If you'll notice, some lights are on more often than others. Like this one. For every number, this lamp is always on. Same with this one, and this one. Then this one's only off for the number 1, and everything else it's on. This one next to it is only off for 1 and 4, and if you keep going through all of these, you'll end up creating something generally known as a truth table. Here's the one I scrawled down on a piece of paper. As you can see, we need to worry about a lot fewer variables when we're controlling for when to turn it off rather than on, so we'll be doing that. But how do we actually control the lamps? Well, for this lamp we can just check if the input equals 1 and turn it off, but this one depends on 2 variables, and we can only check one at a time within the lamp. Well, we simply need to create another condition that works for either 1 or 4. If we choose everything, we'll be able to compare multiple signals at once. And this is where it gets a little confusing, but we just need to engineer a situation where this is true unless our input is 1 or 4. So the way we can do that is to set it to some arbitrary value like, this lamp is on as long as nothing is equal to this, then put some random signals in a constant combinator and add it to our input. So let's say as long as nothing is equal to 10, it'll stay on. If we create a signal with a value of 9 and a signal with a value of 6, then add our input number we want to display to it, guess what? The only time that condition will happen is if our input is 1 or 4, because either one will cause one of those variables to equal 10 and shut off this lamp. This lamp should be off if its input is 1, 2, 3, or 7, so we add another 4 variables of 19, 18, 17, and 13. At least one of them will equal 20 when we add in our display value and turn off this lamp. We use 20 because that way there's no way that it could possibly equal 10 and shut off that other lamp. So we go through these each one by one, setting them in increments of 10 and giving each off condition its own number, except this one, which we can check whether to turn on instead because it requires 2 less variables. Hopefully that makes some amount of sense, but with everything hooked up, we get this. My favorite thing about this is all the new and interesting numbers we've created by overflowing our value past the expected range. So yeah, as soon as we restrict its input from 0 to 9 with a modulus of 10, it works just fine. Just like before, we divide by 10 and can chain in as many digits as we want. Sure beats the old design, but you can probably see why I prefer to use the Nixie Tubes mod. We can make it bigger if we want to, but one thing that's kind of annoying is that it defaults to displaying 0. We can get rid of that by adding in a DC that checks if there's actually any number to display for that digit, and if not, lets through a bunch of variables from a CC that equal exactly 20, 30, and 80, and so on to turn off all the lamps. We'll need to make our tautological lamps have a condition 2 to turn those off, but that's easy. If it wasn't obvious, we're incrementing the numbers with a clock. So what if we wanted to make an actual timer and not just a display? All we gotta do is take this clock and make another DC output a value of 1 whenever this clock ticks 60 times. Then load that into a memory cell as our seconds. We'll use that as the input, and then it's just a matter of converting seconds into minutes, hours, and this is Factorio, so of course we've got to add days. But honestly, 1 digit probably isn't enough. There's some intricacies, but I won't bother explaining them. If you want this thing to tinker with, again, blueprints in the description. I really hate the vanilla lamps here though, so let's get a mod for some flatter lamps. Oh my god, they're so bright. Why? Well, at least we can turn them down in the mod options. There, that's better. Definitely a lot more readable than the other one. Wait, what was this video supposed to be about? Oh yeah, building a printer in Factorio. Well, if you've made it this far, hopefully you'll be able to follow along. Anyway, there's a couple belt printer designs out there, but I really wanted to make one that people could use and input their own custom messages into without needing to hard-code combinators, and that means making something much more complicated. Starting small, how would we even print an image in Factorio? Well, as you saw at the start, we'll be using inserters. Filter inserters more specifically. I'm pretty sure there's some designs that could use controlled belts, but I've decided on filter inserters. The key to all of this is that you can set the filters of filter inserters with a signal, and so theoretically we'll be able to control what it drops on the belts with circuits, as long as it's connected to a chest containing that item. I'm in Sandbox mode right now using these infinity chests, which can be filled with infinite amounts of whatever items you want. The items themselves will be the colors that we have available to create our images. The belts are squares, but they can hold 8 items each. That means if we drop 2 items at a time, we should be able to approximate a pixel, so all of these inserters will be limited to a hand size of 2. I've decided on 8 lanes, which will let me print images 16 pixels tall. Kind of regret not making it 16 belts wide, but I've got to draw the line somewhere. So in theory, if we send a pulse to 16 inserters along those 8 belts at once, we'll be able to make one column of an image. And therein lies the first complication. You may have noticed that the belts need to be all different lengths to actually fit the inserters and chests, but if we send that pulse, the column won't line up at all. We'll need to add some kind of delay to each set of inserters so that they'll all synchronize with the items from the last inserters. If you want to delay data by 1 or 2 ticks, arithmetic combinators are great, but making a longer delay is rather convoluted. That's because we not only need a memory cell to hold the data we're delaying, we also need a combinator to detect if there's anything in the memory cell and then output one continuously. We use that output like a constant combinator to run a clock, and then we'll need another combinator so we can detect when the clock reaches the desired delay. And then we'll use that signal to allow the contents of the memory cell through and reset it. Except since we use the reset signal to let the data through in the first place, we need to scrub it first by taking its inverse with ACs before letting it into the next cell, or else it'll reset itself immediately upon entering the next memory cell. Yeah, it's a lot to deal with, but this means I can program the delay between each set of inserters. So as you can see, now they're waiting, and only dropping when it'll synchronize. Except, upon further scrutiny, it's slightly misaligned. The timing isn't exact, and playing with the delay variables doesn't seem to be alleviating the issue. I'm confident I could have fixed it or redesigned it, but I decided to go for the much simpler plan B, just making all the belts all the same length. It seems like a no-brainer, but it's a trade of complexity versus footprint. There were actually some interesting considerations involved with elongating the belts. Firstly, because the only way to make it longer is to add a bend with 2 belts, the distance between all the inserter columns needs to be an even number. Otherwise, there'd be no way to make them all the same length and still end up horizontal. Secondly, just being the same length isn't everything. They also need to share the same number of turns, and that's because going around a bend, the inner track of the belts moves items faster than the outer track and slightly alters the item's position. The last inserter column shouldn't need any delays, since it's the one we're delaying everything else to match, but unless we add this random bump, the items don't line up. Magic. Not needing to worry about delays should massively simplify sending the actual data to the inserters too. Speaking of, how in the heck are we going to control the inserters? Saying each inserter controls 1 pixel via filters sent by a wire is all well and good conceptually, but how do we actually do that? Well, to make all 16 inserters in a column output its own pixel without interfering with the others, there's no getting around the fact that we'll need 16 unique signals and a decider combinator for each, isolating the input to every inserter so only the signal for that specific pixel can get through to the intended inserter. But to actually output the colors we want, we need to send that item's actual signal to the inserter for it to be able to grab it from the chest. That means we'll need to be able to allow signals like coal, lamps, and sulfur through to multiple inserters and without it interfering with the other inserters. Meaning, we can't just have the combinators outputting one kind of signal, it needs to be able to let anything through. And that's quite a challenge because when it comes to combinators, you either get to output one signal or every signal, and it won't work if we can't isolate only the item we want. It's not like we're gonna make 256 combinators to isolate every possible color signal for each inserter. So how can we possibly ensure that only the signal we want gets through? Well, this is pretty advanced, but I've got 16 different signals here, one for each inserter in a column. We have other columns of inserters, but those are just so we'll be able to drop items quickly enough to actually fill the belts. So don't worry about those, as far as we're concerned, we're printing one column at a time. All 48 inserters will still need their own combinator to isolate the data, but that means we can reuse the same 16 signals from the other two columns of inserters as long as we separate each set from each other. But the secret method to letting only the item we want through is using the each logic signal in a decider combinator. If we do each equals signal 1 output each, that has the magical consequence of checking every input signal for one that equals the value of our signal 1 and outputting it. So if our pixel data signal has a value of 5, it'll reach that combinator and output any signal that also equals 5. So that signal is only for this one inserter in this column, but if we add in a constant combinator and fill it with all the signals of items with values of 1, 2, 3, etc., and connect it to all the inputs of the combinators with green wire to keep it isolated, suddenly if our pixel signal equals 1, it'll check with the data being sent by the constant combinator and see that there is indeed a signal that equals 1, the coal signal. Then it will let the coal signal through and cause that inserter to grab some coal and create a black pixel. It'll also let through any of the pixel signals that equals that as well, but only signals of actual items can be read to set filters, so those don't matter, and it's why we're using so-called virtual signals to carry the pixel data in the first place. It's a bit confusing having the distinction between something like the 1 signal and a signal with a value of 1, but that means that each value of these will have an associated color. So 1 equals black, and 2 equals white, and so on and so on. Again, the importance of this is that the pixel signals are unique to one inserter in a column, while the item signals need to be able to enter multiple ones. But with this, we can program an image column by simply changing the value of those 16 pixel signals. Here you can see I've set up a bunch of constant combinators loaded with data relating to the color of each pixel to make a column. 3 CCs are read at a time to use all 48 inserters, and we've got a clock to iterate over the data. The result is, I've managed to roughly print the letter F as a proof of concept. Except, looking at it, there's gaps between the pixels, and I hate it. I was worried about this when I decided to use only 6 inserters per lane, which has a maximum throughput of about 27 items per second with this hand size, and a red belt moves at 30 items per second. I thought it might be sufficient, but those gaps are way too noticeable, so time to redesign it, yay! One reason I was wary about using 8 inserters is that it would have been outputting more than 30 items per second, which instead of having gaps, would cause the whole belt to clog up and back up the printer, something much worse. However, in an extraordinary stroke of luck, if we make it so our 8 inserters activate only once every 32 frames, the throughput equals exactly 30 items per second. The other reason is that with 4 inserters, if they all drop their items on the belt at the same time, the items dropped by the last inserter won't clear the first inserter in time before the next pulse comes, causing the first inserter to drop in front of it and making the columns end up in the wrong order. Although we can fix that by just sending the data to the last inserter first, and then sending the rest of the data to all the preceding ones with a 1-tick delay between each, basically giving each inserter column its own dedicated tick. Nice and saturated. If all I wanted to do was print a pre-programmed message, this would be it. I just need to hard-code some constant combinators and hook them up on timers to let their data through only when it was their turn. Obviously, I didn't do that, so here we go. So first things first, we've got to deal with how we handle our data, and the first leg of that is this. Remember bit packing? I told you it was important. What we're going to do is fit 8 4-bit numbers into one 32-bit number. 4 bits to store the color value for each pixel is enough to fit 16 colors, which should be sufficient. That means one signal can hold 8 inserters worth of data, but since we're doing this column by column, we'll need 2 signals to create a whole column. All this unholy mess of arithmetic combinators is doing is taking those packed signals and breaking them up into their 16 constituent signals so they can be loaded into the inserters. That means 8 signals every 32 ticks will be sufficient to control all 64 inserters. The fact that we've got to delay our inserter columns by a tick anyways works in our favor here, because now we can use this decoder for all 8 signals, since only 2 will be going in at a time, but on the next tick, the next 2 signals will go in without getting mixed up with the others. Hopefully that makes sense. One issue is how to load that pulse of 16 signals into the correct 16 out of the 64 combinators that control each column. Well, we can make each pair of signals dedicated to a certain column. The red and green signals for the first column, blue and yellow for the next, and so on. If we knew which signal was decoded, we'd be able to use that to put it down the correct channel. The original signals are broken apart at the end and turned into the 16 generic signals, so they're not much use in that state, but if we add something else that allows the original signal through, we can use that to determine which column the signal should be allowed into. It's just a classic, if this signal is present, output everything decider combinator, but the key is to synchronize our data. Since the decoder requires 4 combinators to finish processing the signal into its parts, we'll need an extra 4 combinators to delay the original signal so that they arrive at the same frame and can be used to open the gate to the correct channel. You can see up here how I've got a constant combinator that contains our 8 signals that will comprise one cycle, or enough to print 4 columns. It continuously outputs into 8 different combinators that will isolate and release the signals in pairs when it's their turn to be read. The encoded signals I'm sending equate to 15, 14, etc. descending, and then 0, 1, 2, etc. ascending in binary. It's just like the time division I did in my Factorio City video, where we can use the same wire for lots of different data as long as we give each one its own clock cycle it's allowed to transmit on. There were tons of little tweaks I had to do, the most conspicuous being that I had to give up on it being 16 color, and that's because the way I loaded my data is by detecting that signal. And though I should have 0 through 15 available to me, if the signal is 0, there's nothing to actually detect. So basically I'm limited to 15 different colors as a result. Unless you count nothing as a color, but that should be enough. Seriously, this part took so much tweaking, but it's gotta be perfect. Now actually making the encoded signals is a massive pain, so I've made this abomination. Basically all it does is read what's in the chest and put that through 16 ACs that will multiply that item's signal and give it the appropriate number we assigned it at the printer. So something like coal is 1, red wire is 4, and underground belts are 15. That's sent to another AC that bit shifts that number to the left according to its position, and that's added together with all the other numbers from the 8 chests to create the composite number containing the complete pixel data. Then we can copy that into a signal, and if we put it into the printer, it starts printing everything correctly. It's tedious, but it's at least straightforward. Instead of doing half a column, I upgrade it to do a full 16 pixels and give us 2 numbers. Theoretically, we'll be able to construct whatever image we want to load piece by piece using this. Now on to how I'm actually going to accomplish my dream of being able to load any message into it. Obviously we'll need to use some sort of dynamic memory, which means memory cells, but we'll also want to be able to iterate across all the data so it can be loaded in order. Well, our shift register is perfect for that. If we say that each cell will contain 8 signals, then the same clock that controls the inserters can also be used to advance the shift registers once every 32 ticks, causing the next cell to feed its memory into the reader for the next cycle. If we connect the last cell to the start, we'll create a ring buffer, meaning the printer will repeatedly cycle along the memory we've put into it. I've manually loaded the cells with the values to output all coal for a cycle and all red wires for the next as an example. As long as we can load things into these memory cells, we'll be able to dynamically program the messages into the printer. I decided to expand the encoder chests, and unfortunately there's no getting around to needing 16 combinators for every chest, so it's quite massive. And I'm trying really hard to keep the wires separated, because any crossed wire will be difficult to detect until we load the signal into memory and realize it's off. But this allows us to construct a cycle's worth of signals at once. The first thing I actually use it for is to roughly create this smiley. You can see how iterating across the memory cells allows us to chain together coherent images, even though each cell only contains 4 columns each. Actually loading the cells is the hardest part, however, and that's because of one major feature I want, and that's the ability to have varying image width. The way I'm going to be loading the actual data is that the user will press a button, and on that button press, a pulse of data containing all of the information required to make the requested image will be sent to the printer. Because sending something like the letter A in one button would require 16 signals to contain it, we're going to need to reformat them into the color signals that the printer understands before loading them into the shift registers 8 at a time. The problem is, it would be easy if I forced the width of every image to be in multiples of 4, aka 8 signals, because that's the amount that could fit in one memory cell. Wanting dynamic widths means I need to deal with the prospect that an image might end with only a partially filled memory cell. That means not only do we need to reformat the data, but we also need to detect when to shift the register and start filling up a new one, but also what color the data should be formatted to and in the correct order, knowing that it could be in any of them depending on what was left in the cell when it started. Okay, this is definitely the single most convoluted part of this whole machine. I had to make so many revisions while building it too. So many components were gutted, altered, or fiddled with, making it almost impossible to show the building process coherently. What should happen is that when a user presses the button to load the desired character, all that data will be captured in a memory cell. That memory cell will start a clock, and that clock will be used to iterate across every signal stored in the memory cell. Each signal has its own dedicated combinator that isolates and lets one and only one through when it's that signal's turn, again using time division to schedule the data processing. That allows us to isolate the signal to be reformatted, but then we need to read the contents of the memory cell we're actually loading it into. If there's nothing in the cell, load that signal as red. If there's only a red signal, load green. If green, load blue, and all the way up to the gray signal. We could do that by checking for the red signal, then checking if there's no green signal either. That way our input signal will be allowed down the correct path that multiplies any input signal and outputs the green signal. Once the gray signal's been added, then it's time to shift the cells ahead by sending the reset signal just like the clock would, but only once. Keep in mind that to actually load the cells, it's necessary to stop the main clock from advancing, which I've solved with a constant combinator and a decider combinator that blocks the clock's output from making it through when it's on, so you're free to load the data in peace. One of the many alterations I had to make was needing to filter out all the color signals and reset signals that were leaking through with these ACs set to multiply all the different colors by -1. Since the next AC needs to be able to take in any of the 32 raw data signals as input and turn it into a color signal, if there's any input but that, it'll get added to the green signal and mess up the value. So although we need those signals to know which color our input signal should turn into, and we need to let everything through to allow any of the 32 signals we want through as well, we need to get rid of them on the other side. Then there was the fact that our data was coming too fast, and so I had to add a ton of delays to slow down the rate at which the data was iterated upon, because it took like 4 ticks to actually load the signal into the cell, but the only way to know what color our input should turn it into is by knowing what was already currently in the cell. Without enough of a delay, it would load in another signal before the previous one actually got to the cell, so it wouldn't know what color to turn the current one into. Just lots of headaches and fiddling, but eventually I got something that works. I've even got these lamps that blink when it's busy processing data, and I also added something that blocks the memory cell from receiving more data until it's done processing, so you don't accidentally hit the button twice while it's busy and ruin all the data. Then I added some lamps to the shift registers so you can easily visualize the data loaded into them. It's a ton of combinators, but just remember, all it's doing is holding data sent from the buttons until it can be processed and reformatted before being loaded into the printer's memory. 90% of its mass are combinators that just isolate and remove unwanted signals. After so much effort, now that this part's done, I'm pretty sure that every programmer understands what I mean when I say that it feels wrong that it's actually doing what I wanted it to do. Anyway, we can finally hook it up to the printer's memory, use the encoder to get our special numbers required to make the letter A, which were 16 in total, and put that into 2 constant combinators. Again, the push button creates a signal that allows the data contained in the CCs through as a pulse. That way I'll be able to connect every letter together with the same wire. There it is, the letter A. Only 25 more letters to go. So far I've created a printer that screams, which seems appropriate. Then I decided to program the letter S next, which allows me to create the most important string of letters and the legendary initials of every high score at the arcade. But I want to show the true potential of this printer. I made an image that's a little bit more complicated. This one uses the maximum 16 by 16 resolution that I've designed for, but if you want to make a wider image, you can just use 2 buttons. Then I make the most suspicious image, with only some minor issues. Turns out I was an idiot and had some key combinators set to activate only when a signal was greater than 0, forgetting the fact that it could also be negative. I kinda like the negative numbers though, makes the data indicators more colorful. As I said, this whole thing is a big ring buffer that'll loop data forever, but what if you wanted to get rid of the data that's stored inside? Well, before you had to physically unhook the wire, but I'm adding a decider combinator that will let the shift registers cycle back to the start so long as the explosive signal isn't present. That means if you turn on this constant combinator, it won't be able to loop anymore, and the data that goes out the end will instead disappear. More than that, I can also make the explosive signal activate a clock that rapidly advances the shift registers to speed up the rate at which the data will be cleared. Just don't turn it on while the main clock is also running, because it can irreversibly break the memory cells by giving them a value of -2 on the reset signal, which is unrecoverable. At this point, all that's really left to do is get all the values for each letter and symbol we want to add to the printer. But am I really going to drop items in chests one by one and manually type in the values of 16 signals for each letter? No. To make this actually possible, I wrote this code. Factorio blueprints are JSON files compressed with zlib and then base64 encoded. Most of you probably have no idea what I just said, but it means we can unpack a blueprint string, edit the contents, then repack it and actually have it work in-game. My base blueprint is just 2 connected constant combinators preloaded with all 32 possible signals. From there, all I need to do is input an image via the command line, check it pixel by pixel, and then encode that pixel to a number 1 through 15 and pack it into a 32-bit signed integer, just like we're doing in-game. It goes column by column, slowly replacing all the values of the signals inside of our blueprint before finally finishing and spitting out the finished string. Load that in-game, and it just works. But don't listen to me, listen to the printer. Even with this, making all the images for each letter and converting them to a string one by one still took a couple hours, but it should all be worth it. The font is called Jupiter Crash, by the way. This is why I wanted to use bit packing. To fit all of these pixels just to make the letter A, I would have needed 128 separate signals and 7 constant combinators per letter to fit them all. And that's just for a 16:8 image. I'll be including this code along with all the other blueprints, but keep in mind that the maximum image size is 16:16, and I didn't exactly program it to be user-friendly. It can convert any complex images, but if your blacks aren't exactly 0 and your whites aren't exactly 255, it won't know what to do. Same with everything else, and a couple other arbitrary color values I chose, like 255, 130, 70 to make orange, so just be aware of that if you want to use it. Otherwise you'll have to use the very tedious in-game option I built, but that's why I made it. So after all that, we can now finally load any message we want into memory and watch it drift along the belts. But there's one more feature I want to add. I just can't stop myself. All of the text is white, but it seems like such a waste when we have so many more colors available. Instead of hard-coding 15 different versions of text for each color, I can instead intercept the data before it gets to the formatter, then break apart each signal into its 8 pixel values, and if we find anything that equals 2, remember 2 is the value denoting white, we can then add a constant to it. If we add 1 to that value, suddenly the text turns red. If we add 2, green, and so on and so forth. Then we just need to shift each bit of pixel data back to its appropriate position, put it back together, and then send it to the formatter. If we make a latch like I showed you before, we can load what constant we need to add to turn it into that color and put it into a memory cell. By pressing the buttons, we'll set it to that color, and anything loaded into the printer memory will be adjusted. Pretty neat, right? Thanks, math. That's basically it. I added a bunch more images just for the fun of it, but it's ready to use. Since I made this with the intention for other people to be able to use as well, I'll go over how to load the messages again in case you didn't get it already. First, you'll need to pause the clock by turning on this Combinator. If you have the push buttons mod, which you should to actually be able to use this thing, you can just press F to toggle it. Now that it's paused, you can start loading your data. It's pretty simple. Select the color you want, and then press the character you want. Just make sure you don't screw up because there's no backspace feature. Though the time it takes the machine to process each letter should give you plenty of time to think about your next input. This is unfortunately the consequence of needing to reformat the data. One tick to go through a Combinator sure adds up if you've got 32 signals that each need 6 ticks to process. Sitting here writing this script, I've actually thought of how I could have cut down the processing time by at least a factor of 3, but I've just gotta walk away, accept that it's good enough, and resist the urge to completely redesign this thing. The best I did was add a W signal to the data that tells the reformatter the width and that it doesn't need to iterate across all 32 signals for an image 2 pixels wide. Anyway, as soon as you've loaded your message, unpause the clock and wait for the data to cycle around. I made it come standard with quite a bit of memory, and this is the scariest thing you'll need to do as a user, but if you want a smaller message to loop, then you'll need to unhook the last memory cell containing your data and then wire it into the top row of power poles. Make sure it's the only cell hooked up to those poles. That means you'll need to unhook whatever the last memory cell that used to be the endpoint was. There we go, now it'll loop properly and you can sit back and relax as you watch your custom messages drift by, stunning all who visit your factory with your sumptuous uses of circuits. Then if you want to write a new message, pause it again and turn on the clear signal, watching all your data fly away until you're left with nothing but empty cells, ready for whatever wisdom you've got to share next. Just make sure that if you're trying to input a larger message, you've got the memory to handle it. Ah, isn't that beautiful? One last thing though. You might remember that we're using infinity chests. Obviously you don't have those in the real game unless you cheat, so let's make this thing work normally. To do that, we'll swap out our infinity chests for requester chests. Unfortunately, their capacity isn't the greatest, but with a good bot network, it should be enough to keep pace with the printer. Set the requests to include all of our colors, and the bots will try to keep them full. We'll want to reuse what we printed, so once the message has made its rounds, we'll route it back in and stuff it into a bunch of provider chests nearby so the logistics bots can quickly refill the requester chests. And there it is, my take on a belt printer, and hopefully something you can have some fun with. I still wish I made it 32 pixels tall. Final roll call, image data, font colorizer, data reformatter, memory bank, memory controller, data input, data decoder, inserter controller, item data, and finally the inserters. Thanks for watching. I doubt any but the most dedicated Factorio enthusiasts made it this far, but I'd like once again to thank my patrons. This video is a bit different from my usual stuff, and it kind of ended up as a bizarre chimera between tutorial and tour, but hopefully you found it interesting. I mean, obviously you did if you're still watching, but you know what I mean. Once again, blueprints in the description, and... wait, what?